Yeah.
Okay, hello everyone. We are from Group 3, and this is our final assignment, which is the Dynamics of Gaza Water Management Case, which consists of Faris, Hanif, Muhammad Tahir, Nabil Rahman, me, Rifki, and Taza Kharezi. This is the table of contents from the background until conclusion. This is the background where the Gaza's water sector faces a systemic collapse as unsustainable extraction and poor infrastructure drive a crisis through 2050, there are three pillars of this crisis, which is the first one is environment and resource exhaustion, the public health emergency, and economic and land competition. The strategic goal of this case is to model a structural solution between now and 2050, which requires balancing the three things, which is infrastructure, innovation, and also policy. This is the SEQ of the case, which since 1975, the Gaza Strip has relied on one single primary resource, which is groundwater aquifer, which supports a flourishing agricultural sector, which is citrus, olives, and wheat. And the second one is Gaza is one of the most densely populated regions on Earth. There was a historical understanding on how the water system functioned with an objective to manage the supply for the medium, which is 2005, and the long term is 2050. The conclusion is the stability of the system has been broken by a triple threat of factors, which is the one that I mentioned before, which is physical exhaustion, public health collapse, and resource competition. And the key question to this is how can the Gaza Strip develop a structural solution that balances population growth and urban development with the preservation of the aquifer and the survival of the agricultural sector through 2050?
Okay, based on the identified issues, we have a stakeholder analysis and we map the stakeholders based on their needs, interests, and also their power. When we have like Palestinian Water Authority, we have the residents of the Gaza Strip and also the local industrial sector. And next, from the actor, we now identify the stakeholders through an actor analysis matrix. And this is to define their roles and also their influence. And we have the highest quadrant is quadrant one, and the actors are Palestinian Water Authority and Israeli water and government authorities that needs to be prioritized in our analysis. Next. And here are the CLD of population and land allocation. Next. Here are for the groundwater and also for the water supply and demand. Next. This is for the household water and household land usage. Next. This is for the industrial water and also for the business land usage. Next. And the water usage and also the agricultural land usage. Next.
From all of those submodules shown before, we have merged them into one big joint CLD as shown in this slide. Unlike the separated submodules, this joint CLD helps us to understand the relationship between all variables in the model in one visualization. Next. Okay. Besides the joint CLD, we also made a system diagram which consists of 7 actors, problem owners, objectives, stakeholders, internal and external factors, and of course the system model or CLD itself. This diagram helps us to understand the connection between those components in the model. Next. Here are the stock and flow diagram for population and land allocation. Next. And these are for groundwater and water supply and demand. Next. And these two are for household water and household land usage. Next. Here are for the industrial and business land usage. Next. Here are the SFDs for agricultural water and agricultural land usage. Next.
And then after we develop the model, we doing the verification and validation. And after we're doing the unit check, the result is okay for both model and units, reflecting that the units are consistent and no errors are found in the model of Hansen. And then the next one is integration error test. So we're doing the different time steps for the model. The first one is one for reference, which is the actual, and then for the comparison, we're doing 0.125 for comparison. And it found that the average margin of error result it exhibits unmatched precision in population forecasting, yet reveals that the greatest study risk lies in the 29% margin of error for FL land, recording a highly adaptive approach to urban and agricultural policy through 2050. Next. And then for the model validation, we have several variables to be the first one is population and then groundwater volume, groundwater level, and housing area and business area. Despite a mean margin of error of 1979%, the model remains validated because the error caused by external factors that fall outside the model scope rather than flaws in the model's internal logic. Next. And then the last validation is extreme condition, where we input the extreme condition, which is zero rate in the birth rate, and we have the hypothesis of the population will always decline throughout the years because of the equation. And the result, reflecting the similarity with our hypothesis, with births dropping to zero because the birth input is zero per year. Next.
Scenario development is developed using high impact and high uncertainty variables derived from the impact uncertainty matrix. Scenario development is based on the impact uncertainty matrix, which focus on variables that have both high impact and high uncertainty. These variables play a critical role in system performance, but are difficult to predict. And based on this approach, the scenario always run a shortfall immigration efficiency per year, percentage of house with sewage connection, and area per house as the key source of uncertainty. Okay, next. And the selected variable are mapped into three scenarios to represent different possible conditions. With the input variable, there's efficiency per year, percentage house with sewage, area per house, and shortfall immigration. With business as usual, for the efficiency per year, it's 1.5%, and percentage of house with sewage is 46%, and area per house is 208 and 5 meter, and shortfall immigration is 0.0125 until 0.2. And for the PET2 is for the efficiency per year, there's 3%, and percentage house with sewage is 85%, and area per house is decreased to 150 meter, and shortfall immigration with total 0.005 until 0.1 120, and then here for the pet 3 and pet 2 and pet 3. Okay, next. And each scenario represents a distinct developed path under different assumed condition from the best case to the worst case outcome. With the pet 1, the resilience modernization represents the best case scenario where higher efficiency and strong sewage infrastructure improve living condition and keep immigration low. And for the PET 2, the industrial paradox shows a trade-off scenario. Industrial growth is prioritized, but agricultural efficiency decline, leading to unequal water allocation and moderate immigration. And for the PET 3, the environmental catastrophe reflect the worst case outcome: infrastructure failure and urban sprawl rivalry degrade the environment, driving extreme immigration. Next. And here for the business as usual against scenario comparison on population variable. Okay, next. And here for the business as usual against scenario comparison on the weather variable. Okay, next. And here for the business as usual against scenario comparison on the water variables too. Next. And here for the industrial water supply, working population, and industrial water demand variables.
Okay, here business as usual against scenario comparison on agricultural water variables. Next. Here is business as usual against scenario comparison on housing land variables. Next. Here are business as usual against scenario comparison on business land variables. Next. Here are business as usual against scenarios comparison on agricultural land variables. Next. Okay, so based on the base model results, Gaza water crisis is driven by three main root causes. First, rapid population growth continues to increase water demand while available supply keep declining. Second, groundwater levels are steadily decreasing due to heavy use across domestic, industrial, and agricultural sectors, with limited alternative water source. Third, limit land availability and competing land use prevent optimal and land allocation. This root cause form the basis for the policy improvement explored in the scenarios. Next. So in each scenario, two policies are implemented with each policy designed to directly target one key variable in the system. This structure allows us to clearly observe the causal impact of each policy intervention on the model outcomes and compare their effectiveness across the scenarios. Next.
Okay, this is the policy formulation for scenario 1, which is the tech resilient Gaza imposed policy. The plan action is to 1, mandate vertical housing development, 2 is to implement family planning programs, and 3 is to integrate smart urban planning. These impacts two things, which is housing area demand and birth. Impacts on the housing area demand. How? As the slower growth of housing area demand due to more compact housing development. The second is the birth is the lower number of births, reducing long-term population pressure. Second one is the plan action for scenario 2 is the industrial paradox. First is to apply industrial water efficiency standards to improve annual water use efficiency. Second one is to introduce social stability incentive. 3 is to manage industrial growth impacts. And the impact is towards irrigated water consumption and net emigration. The impact towards irrigated water consumption is increased irrigated water consumption despite efficiency gains, indicating a rebound effect. And towards net emigration is reduced net emigration pressure through improved social stability. For scenario 3, which is infrastructure deterioration, the planned action is to upgrade and expand sewage networks. Second one is to preserve agricultural land, and the third one is to control housing expansion. The impact is towards the cesspit is to reduce cesspit usage due to expanded sewage network coverage, and the second one is towards housing area demand is to lower housing area demand through controlled housing expansion and land preservation.
Okay, now we have the graphics for the business as usual versus the scenarios comparison on population and also water variables. Next. And here are the comparison on the water variables. Next. And this is for the comparison for the land variables. Next. And now we have the result from the three scenario. And for this first scenario, we have a minus 40% in housing area demand and also minus 15% in birth. And for the second scenario, we have increasing of 2% in irrigated water consumption and also minus 30% in net emigration. For the third scenario, we have a 20% increase in cesspit and minus 25% in housing area demand. Next.
And then after the two scenarios that we have developed, each scenario explored strategic and sectional policies. We found that population growth and horizontal expansion raised housing pressure, and then industrial growth increased water stress. And other than that, socioeconomic instability drives emigration. Means that the effectiveness and visibility through scenario analysis might improve the condition of the other after the case study. It shows that there is a need to implement different stakeholders and joint methodology to ensure sustainable management of water resource. Next. Here's the reference that we use next. And the fancy files and the building of fancy files next. And that will be all from you three. Thank you so much for your attention.